Everyone, good morning. Let's start the today's lecture. So let me give you a quick recap that we have done in our last class. So we have wrapped up the probability, right? In the last discussion, I think we took two sessions for the probability. We talked about the basic probability. We solved some probability problems as well. And in the last session, we discussed about the probability distribution, right? So like those things are very helpful, when we try to solve problems related to statistics, inferential statistics and machine learning problems. We'll be seeing their applications in the future. Uh, so let's start with today's lecture. Let me share my screen. Okay, I'm gonna share my screen. Give me a second. I hope it's visible to all of you. Okay, so today's discussion is around the sampling and the sampling distribution. Okay, so it's one of the important topic, and I would say the most important one for machine learning, right? Because we'll be dealing with a lot of problems where you need sampling, right? Because you'll be having data that can be imbalanced, right? Maybe like the data set is quite huge, right? That you are not able to, use in your system directly, right? So for that, in that case, you will be taking samples out of it. And like in the initial part of our course, right, we discussed about the population and sample, right? So we'll be seeing that in detail today. So let's start. Okay. So let's start with the introduction of sampling first, right? We have already discussed it in brief, right? But it was in very early lectures, right? And I'm hoping that you are not aware. Okay, so let's start with the very basic. So what is sampling, right? So let's start with the definition of it. So sampling is the process of selecting a subset, okay, or a sample. You remember sample from the probability classes, right? What was the sample there? So it was the subset of the total possible outcomes, right? The sample space that we were taking, right? Similarly, it is a subset from a large population. Okay. And why we do that? To make statistical inferencing, right? Statistical inferences about the population. Okay. So let me repeat it again. Sampling is the process of selecting a subset from a larger population to make statistical inferences about the population, or to make some judgments about the population, right? Because it's very difficult to deal with the large population, right? Because like it's difficult to process it first, and again, if you want to analyze it, it'll be again a very challenging task, right? That's why we take sample of it, subset of it. There are a lot of available methods to do the sampling, and we'll be studying them in detail today. Okay, so let's talk about some importances of sampling, right? Especially in data science sector. So as I told you, processing a very large data set is a time consuming task, first of all, but a very costly affair as well, right? Because let's say if you want to load a terabyte file on your laptop, it may not be possible because you don't have that kind of memory, right? You don't have that kind of codes to process that, right? So that's why it's the sampling makes your operations cost effective. Okay, so that's one of the important thing about the sampling, right? So it's making your data processing or any operation that you are trying to perform cost effective, right? Second thing is the time efficiency, right? So when again, like the reading part was there. When you read a file, it will take their sweet time to read, right? Because it's a very big file. But again, when you perform the analysis, right, it's easy to perform the analysis on a small subset, right? Rather than doing it on a very large population or a very large data set. Okay. Then again, the feasibility, right? As I told you, right, if the population is very large, right? So the feasibility is not there, right? Because with the sampling, it's feasible to load that file in a system and perform some operations. Okay. Now let's talk about the differences between the population and sample. Okay. So again, like we have a brief idea about it, right? Because we have already discussed it long back. So population in this case, so what population represents, right? Population represents entire group, right? that are going to be studied or that are being studied. Okay, but a sample, right? A sample is a subset of the population that is used for analysis, right? We cannot analyze the whole population. Let's say we are talking about the humans on Earth, right? So it'll be very difficult to analyze every human on the Earth. What we can do to do this analysis, we can take the sample out of it, right? But that sample should be, good enough so that we can perform the analysis that we want to perform. Okay, there are some rules due to the sampling that we'll be studying about in the upcoming slides. Okay, so yeah, so now there are two more terms. Okay, let me activate my fan. Okay, now there are two more terms: parameter and statistic. Okay, so what is a parameter, right? So like you remember when we started our journey for this statistics for data science, we talked about these two things, parameter and statistic, right? A parameter describes a characteristic of the population. Okay, for example, the population mean, right? We represent mean with the mu. All of you must have like must know this, right? We The second parameter could be, or the characteristic of a population could be, population variance, and I hope all of you are aware about it, right? And then what is a statistic, right? Statistic is nothing but again the characteristic of a sample. Okay, so let's say it's almost the same thing. So here we represent like sample mean, right? Sample variance. So instead of population, we are calling as a sample mean and sample variance, right? So these two values could be same or could be different, right? It depends on the sample that we have taken out of our population. So in the case of population, it will be mu, but in the case of sample, it will be x bar. So these are the you know the type of, or type of representing basically, right? So whenever we, like, even in the upcoming slides, right, if I'm saying mu, it means we are talking about the population mean. Okay, and if I'm saying x bar, it means we are talking about the sample mean. Okay, similarly, if I'm saying sigma square, okay, it means we are talking about the population variance. If I'm saying s square, it means I'm talking about the sample variance. Okay, so now let's move to the next slide. Okay, so now, like as I had mentioned, there are multiple types of techniques to do the sampling, right? And we'll be studying them in detail one by one. Okay, so let's start with the first methods. Broadly, only two categories are there. One is the probability sampling, and another one is the non-probability sampling. Okay, but under the probability sampling and the non-probability sampling, there are many methods. Okay, so let's start with the probability sampling first. Okay, so what is the probability sampling? Probability sampling or the random sampling methods, right? So, okay, so what it is, right? Probability sampling ensures that every element in the population has a known chance of being selected. Okay, so what does it mean? So let's say we have uh, 1 second. Yeah. So let's say we have a set where we have 1, 2, 3, 4, and 5. So here, out of this sample space, each and every element is having equal chance of getting selected. If when we are talking about the random sampling methods or the probability sampling method, right? Got it? So again, so each of these elements, so from this sample or the population, let's say this is the population, okay? Okay, so each and every element is having equal chance of being selected. Okay, Hey Rakesh, so we were discussing about the sampling methods and strategies. Okay, so we have just started the first sampling method, that is the probability sampling. Okay, if you have any doubt, you can stop me anywhere and we can discuss that. Okay, there's a okay, cool. Okay, yeah. So let me tell you the probability sampling again. Probability sampling is a method where every element in the population has a known and non-zero chance of being selected. Okay, this technique ensures the randomness, reducing selection bias, and allowing for generalization of results to the entire population. Okay, so now the okay, so one important thing here is to focus the selection bias. So what is the selection bias? So you remember when we like started our lectures, right? We talked about one very important thing, that is the selection bias. Okay, so what is the selection bias? So let's say if I'm extracting data from a population and I'm selecting it only for the male population. Okay, so it means it is gender biased, right? Or let's say from this population 1, 2, 3, 4, 5, I am just selecting even numbers. So again, this is having some kind of bias because it's only because we are just selecting even numbers here, right? So there should not be any selection bias, right? So that thing, your probability sampling ensures, right? There's no bias in your sampling method. Okay. Now let's move to the next slide. Okay, so first method in this under the probability sampling is the simple random sampling. It's one of the easiest method, right? Let's discuss about it. Okay, so in simple random sampling or SRS, every member of the population has an equal chance of being selected. So it's like the definition only, right? That we discussed about the probability sampling, right? So in this case, every member of the population has an equal chance of being selected. Okay, second, selection is done using the random methods like lottery system or random number generators. Okay, so there's no specified method here, right? So it's like a pool, right? Let's say we have a sack with a lot of balls, right? Numbered from 1 to infinity. Okay, so chance of here each and every one is having equal chance, right, of being selected, right? So similarly, it's kind of a lottery system. I'm drawing the balls from that sack. Okay, so this is the simplest method, that is nothing but the simple random sampling. Okay, you can take an example here. The example is, suppose a university wants to survey students about their satisfaction levels. Okay, so they can randomly select 200 students from the entire student body and take the survey. Okay, but again, these students should not be selected based on some condition. If the condition is there, it means you are introducing some selection bias, and again you are not following the principle of the probability sampling, right? Because according to the principle of probability sampling, each and every element should have equal chance of being selected, and it should be non-zero. Okay, let's say if one particular is having zero chance of getting selected, it means it is biased for that particular element, right? It will never be selected. Okay. So now what are the advantages of the simple random sampling? Okay, so advantages are it minimizes the bias, right? See, again, in the real world, you cannot reduce the bias completely. Bias is like the irreducible error, right? It'll always be there. We can minimize it, but we cannot diminish the effect of bias. Okay. If you perform any sampling or you do anything, there will be some kind of bias even in your real life scenario. Okay, now what is the next advantage in this type of sampling? It is easy to implement with smaller population. Okay, now let's talk about the disadvantages of this sampling method. So the disadvantages are, it requires a complete list of the population. Okay. If it is not there, right, then again the same thing. Each and every element will not be having the equal chance of getting selected. Right. So all the population should be present there. Okay. Now again, the problem here is, so it just a lot of things, right? I mean, the example that we took, right? The balls in a sack, right? So your balls are not grouped properly. I mean, they don't have any kind of identification there, right? I'll tell you why I'm saying that. So it's very difficult to, represent subgroups and all there, right? Because we don't have that kind of categorization there, right? So we have the more advanced method, right? So that can help us basically to create better samples out of our population. Okay. So the next in line is, and my favorite one is the stratified sampling. Okay, and we use it a lot. Okay, especially in the case of imbalanced data set, right? And in general, right, the data sets are not imbalanced or balanced, right? So if you took like take if you try to solve any classification problem, so most of the time one of your class will be having the majority there, and the negative class, right, will be having a very least effect, right? So let's talk about a very simple example, the cancer patients, right? So everyone is not like affected by cancer, right? So if you take the entire population and make two classes, cancer patient, non-cancer patient, so this particular data is imbalanced, right? Because the sample size of your cancer patient compared to your non-cancer patient is very small. Okay, it could be like 1 or 2%. Maybe I'm exaggerating it, could be less than that. Okay, or it could be more than that, right? We have not checked the facts, so we cannot promise. Okay, so let's discuss about the stratified sampling. Okay, so what is the stratified sampling? Right, stratified sampling, how it works, right? The population is divided into subgroups. Okay, and we call each group subgroup as strata. Okay, it's another name of the subgroup, right? So the population is divided into subgroups based on a specific characteristic. Okay, it could be age, gender, income level, or any category present in your data set, right? It could be, based on the profession, salary range, anything, right? So we divide the population into multiple subgroups, and then out of those subgroups, a random sample is taken from each stratum proportionally. Okay. So what does it mean? Okay. So from each sample, right, we are taking equal proportion. Okay. So let's say we have created multiple groups using age. Right now, you have multiple small samples, right? So then from each sample, or let's not call it as a sample because it's part of the population only. We have just divided the population using some characteristic, right? So let's say we have created 10 age groups out of the population. Okay. Now from the each age group, we will be taking some data or a sample, right, proportionally. Okay. Example, a company surveys employee ensuring representation from all departments, right? So now here the division is happening. The subgroups are like we are creating the subgroups using the department. So in this case, the department can be HR, IT, finance, etc. Okay. So from each department, we'll be taking some number of employees, right? Again, we are using the previous algorithm only, but what we have done, we have divided we have divided our data into multiple subgroups. So now each group is having equal chance of getting selected. Okay, because so in the last algorithm, what would happen? Maybe while retrieving the data, while creating the sample, you get more number of people from one particular department, but very few people from the other departments, right? So what will happen? You will be having a very limited information from the departments where you're having very less sound, right? So that's why this algorithm is better than the simple random sampling. Okay, so let's talk about the advantages of stratified sampling. Okay, so it ensures representation of all subgroups, right? As we discussed in the definition, right? When I mentioned that we'll be dividing the population according to the characteristic, right? So there could be many subgroups if we want to, right? But generally we choose a particular characteristic and divide it and then select the random sample from each subgroup. Okay. Now, what is the second advantage in this case? So it will give you more precise results than simple random sampling as we discussed. Okay. So now what are the disadvantages in this case? Okay. So the disadvantages are it requires prior knowledge of population characteristic, right? Let's say you're not aware about the age distribution, gender, income level, right? Then you'll not be able to create the subgroup, right? Because you don't know it, right? So it requires the prior knowledge about the of population, okay? And the second thing can be it's a little complex to implement, right? So with the help of Python, we can do it, but in general, it's a little complex to implement. Okay, let's move to the next type of sampling. That is nothing but the systematic sampling. Okay, so what is a systematic sampling? Okay, so in this case, every kth individual is selected from a list after randomly choosing a starting point. Okay, so it's little confusing. Let me take an example to explain it. Okay, so the example is a researcher selects every 10th visitor entering a shopping mall for a survey. Okay, so you're imagining, right? So he's not picking every individual that is coming to the mall, right? He's just picking every 10th individual that is coming to the mall. So it's a type of systematic sampling because it has a system that is it's following, right? Now there are some disadvantages and advantages related to this algorithm. Let's talk about that. Okay, so the first advantage is it is easier than simple random sampling, right? Because we are just picking a particular guy, right, every time, right, based on a time interval or any predefined criteria that the individual have decided, like that we have decided. Okay, it provides even coverage across the population. Okay, now, what is the disadvantage? So, if there's a hidden pattern, right, in the population, there are chances of bias. Okay, so that's why it's not that great algorithm. So that's why, like when I was trying to explain that Stratified is one of my favorite, it works really well. Okay, so now let's talk about one very interesting sampling strategy, and it's again as powerful as the stratified sampling. Okay, so it is the cluster sampling. Okay, so in this case, the population is divided into the clusters, usually based on the geography or the other natural groupings, right? So we create cluster among the population. Okay, now it could be again any characteristic that you want to use or you want to create cluster. Okay, so like instead of creating subgroups like stratified sampling, here we'll be creating the clusters. Okay, so now again, out of all those clusters, a few clusters are randomly selected and all individuals within those clusters are surveyed. Okay, N- for an example, a health department selects 5 out of 50 cities randomly and surveys all hospitals within those 5 cities. Okay, so here in this case, 50 cities are there are 50 clusters and each cluster is representing a city. Okay, and what we did, we randomly selected 5 clusters out of the 50 clusters. Okay, and now what is happening? Every individual from those 50 cities, okay, we'll be studying. Okay, or here in this case, individual is a hospital. Okay, got it? Good. Now let's talk about the advantages and disadvantages of this algorithm uh, or the method, right? So the advantages are it is a cost effective for large population. Let's say when we have very, very large population, right? So it's easy because we're reducing it by a very big margin, right? The size of the sample, right? Useful when population is spread across a wide area. Okay. Now what are the disadvantages? Okay. Higher sampling error compared to stratified sampling. You remember I told you, right? Stratified sampling is one of the best, right? So yeah, so there are high chances of sampling error compared to stratified sampling. Okay. And the second thing, selected clusters may not represent the entire population, right? Remember when we were performing sampling using the stratified sampling, we were choosing everyone from each subgroup, right? But here that's not same thing is not happening. We are even after creating n number of clusters, we are not picking random sample from each and every cluster, right? But what we are doing, we are picking random clusters, right? Instead of picking random samples from the clusters, right? So there are high chances that we may not be selecting or we may not be able to represent the entire population. Okay, cool. Now let's move to the multi-stage sampling. But before that, we will take a break of 2 minutes. I'll have some water and come. Okay. Meanwhile, if you have any doubt, you can write it. Okay. So let's start with the another type of sampling method is okay, that is multi-stage sampling. So far we have studied about four types of sampling method. Okay. So let me give you a quick recap. We talked about the simple random sampling. We talked about the stratified sampling. We talked about the systematic sampling. We talked about the cluster sampling. And so far, the best one is the stratified sampling. And you will be seeing a lot of application of stratified sampling and be when you will be solving the machine learning use cases. Okay, or any data science use cases. Okay, now let's talk about the multi-stage sampling. Okay, so what is the multi-stage sampling? So it's a combination of different probability sampling techniques. Okay, so let's example, right? So we are, so like it's happening in stages. Okay, so let's say in the first stage, we are selecting states. Okay, or out of the population, we are targeting a particular bigger segment first. Okay, so in this case, we are taking an example of states. Right now, among the states, we are selecting districts. Okay. Now, among the districts, right, we are selecting the schools. Sorry. And among the schools, we are selecting the students. Okay. Now, for each entity, you can use a different sampling method. Okay. So, what are the advantages of this type of sampling, right? It's very useful for large scale surveys, right? When you have a very, very large sample, right? Then in that scenario, in that case, you can use this type of sampling, right? And again, so here, no one is stopping you to use the same sampling method at each entity, right? Or if you want to, let's say you have something very simple, then you can go ahead with a very simple sampling method, right? That's the beauty of this sampling method, right? And it reduces cost and time, right? And what are the disadvantages? So the most common disadvantage for the sampling method is the complexity. Okay, it's little complex to implement, right? And each stage adds potential sampling error because, as I told you, the algorithms are not perfect. They'll be having some sampling error and the bias. Okay, so at every step you will be introducing bias, right? So that's the major problem with the algorithm. Okay, so now let's move to the next section. That is the second part of the sampling or second type of the sampling, right? That is the non-probability sampling, right? In the starting, right, we discussed there are two types of sampling broadly: probability-based sampling or the non-probability-based sampling. And among these two, there are multiple methods, right? So we discussed total 5 methods under the probability sampling method, right? Let me, give you again a quick recap. The one was the simple random sampling, stratified sampling, systematic sampling, cluster sampling, and the multi-stage sampling, right? And among all the 5, right, the best one was the stratified sampling. I'm not introducing the bias for the particular algorithm. I like it personally, right? So there could be some bias in your mind because of me, right? But it depends on the use case that you're trying to solve, right? So better choose the algorithm or the method that perfectly suits your problem statement, right? So like when you're deciding, right, which one to choose, so choose it carefully, right? Okay, now let's talk about the non-probability sampling. Okay, so what is a non-probability sampling? Non-probability sampling methods do not provide every individual in the population with a known or equal chance of being selected. Right? I think the definition is quite clear because we discussed about the probability sampling. In case of probability sampling, each and every element was having equal chance of being selected, right? And the non-zero chances, right? But in this case, every individual in the population with a non or equal, it does not have equal chance of being selected. Okay, so these methods are often used when probability sampling is impractical, right? So it could be because of time, cost, or accessibility constraints, right? So see, there will always be some constraint, right? Maybe you don't have time to perform the sampling, you don't have cost to perform the sampling, right? Because again, sampling is not an easy thing to do because if you're dealing with a very large population, it requires a good amount of hardware to process that data. Okay, but again, as we discussed, it can introduce some bias and it will limit the generalizability in your sample. Okay, so these are the disadvantages of the non-probability sampling. Now let's talk about the methods under the non-probability sampling. How can we perform? Okay, so the first one here in this case is the convenience sampling. Okay, so what is the convenience sampling? So selecting individuals who are easily accessible. I think it's very clear from the name only, convenience, right? So convenience is like easy, right? So in this case, the individuals who are easily accessible. Okay, for an example, a researcher interviews people at a nearby shopping center. Okay, now the thing is like for him, the people at the nearby shopping centers were like easily accessible, right? Now he doesn't have to go very far, right? So now what could be the challenges? Maybe the neighborhood that he is living, right? It may not be that rich or having talented individuals, or could there could be any bias there, right? Any particular type of community living there, right? So what is happening in this case? You are introducing the selection bias, right? Maybe you are not able to generalize your sample process probably generalize your sample properly. Okay, so that is one of the biggest problem with the convenience sampling. So let's talk about the advantages quickly. So advantages, as I mentioned in the definition only, quick and easy to conduct and very low cost, right? You don't have to travel very far, right? Or maybe like the steps that you are taking, right? For that you don't have to spend too much. Okay, as we mentioned, it is convenience. Now, disadvantages, when we were discussing the example, I told you that there are there are very high risk of bias in this case, right? Because the area that you are in, or maybe the particular community, or any part of the population that you're picking, may be having one type of individuals, right? So that could introduce bias in your sample. Okay. And again, the results may not be generalizable. Okay, because again, same thing, right? The sample that you took can be from a same community, same type of individuals. That is the biggest risk in this kind of in this method. Okay. Now, in this series, the next sampling method is the judgmental or the purposive sampling. Okay. So here what happens, the researcher selects individuals based on their judgment of who will provide the best information. Okay. Now you can easily get the idea, right? What is happening here? Okay. So let's discuss it through the example. Okay. So the example is a medical study selects only experienced doctors for expert opinions. Right? So now what is happening, right? Maybe a doctor specialized in a particular sector can give you the better guidance for that particular topic that we're talking about. But again, the generalization is not happening here. And again, some sort of bias is there, right? Okay. So let's talk about the advantages useful for a specialized research, right? So let's say if I'm performing research for a particular topic, okay, so then this kind of information can be helpful for me. But if I'm picking a generalized sample, right, then it's not the right sample for me. Okay. Now focus is on, again, second advantage is the focus is on the relevant subject, right? So it's not like we are not picking any random data, right? We are targeting the targeted individuals, right? Okay. Now what are the disadvantages? Same as the other algorithm, it will be subjective and prone to bias, right? As I discussed the example, right? Results may not be representative, right? It cannot represent the entire population. Okay. So it can represent the population of the experienced doctor, but not the all the doctors. Okay. Okay. What is the third type in this series? Okay, the third type is the quota sampling. Okay. I think it's self-explanatory according to the name, but let's talk about it. Okay, so what is the quota sampling? Okay, so similar to stratified sampling, but here in this case, participants are not selected randomly. Okay, so it seems as the stratified sampling, we'll be creating subgroups, but we'll not be selecting the participants or the individuals randomly out of those subgroups. Okay, yeah. So, example is a survey ensures equal representation of men and women, but selects participants non-random. Okay. So here we have created two groups according to the gender, but the participation, the sample that we're selecting out of those two subgroups are not randomly. Right. So what is happening, right? Each man is not having equal chance of getting selected. Maybe. So let's talk about the problems of this algorithm or the method in detail in when we discuss about the advantages and disadvantages, right? So let's start with the first advantages. So it ensures the presentation of key subgroups, right? So as we discussed in the stratified sampling, right, and in the quota sampling, each subgroup will be having some representation, right? But okay, let's talk about the disadvantages later. Let's finish the advantages. So it is faster and cheaper than stratified sampling because here we are not selecting the participants randomly. Random sampling requires some computation power, but in this case it will be little cheaper. Okay, disadvantages. So right, as mentioned in the algorithm only, the participants are not selected randomly. So it means there will be a selection bias, right? And results may not be statistically valid, right? Because again, it's the sample that we have chosen, right? It's not randomly selected. It could be targeting a particular segment, highly paid individuals, right? Maybe the experienced doctors, right? Or maybe very senior folks, right? So this problem will always be there if you are not selecting the sample randomly. Okay, cool. Now let's talk about the next type of non-probability sampling, that is the snowball sampling. So what is the snowball sampling? So snowball sampling is like you know how it works, like so existing participants recruit future participants. Okay, so it's very interesting, right? So here, you know what is like, you can see what is happening. We have some existing participants that are basically recruiting the future participants. Okay, for an example, so it used for researching hard to reach populations, right? Like drug users, okay, or undocumented workers. Okay, obviously no drug user will come and say, okay, I'm a drug user, right? So, but the drug user population, like they have some sort of connection, right? They know the other drug users, right? So what they can do, they can pick the other drug users or the undocumented workers, right? Because they don't have any documentation, it's very difficult to find them, right? But because of the union and the relationship, right? Workers knows the other workers as well, right? So they can choose the undocumented workers, right? So what are the advantages and disadvantages of the algorithm, right? So advantages are it helps find participant in the niche populations, right? Uh, it is useful for the exploratory research, right? Because as I mentioned, right, it's very difficult to find a particular population, right, or particular community, right, that is not detectable, right? Like the drug users, like they hide themselves, right? They will not come in public and say I'm a drug user. Okay. Now, disadvantage is high risk of bias, you know, and it's clearly evident from here, right? We are picking a particular community, right? So it's highly biased, okay? And sample may not be representative, right? Because you are picking the individuals, right? And you don't have any random sampling here. You're not selecting anything randomly. So chances of selecting that particular user is very high, and maybe someone or maybe many from that particular population have chances zero of being selected, right? So this is the biggest problem in this algorithm. Okay, now let's summarize. Let's talk about the key differences between the probability and the non-probability sampling. I want to give you guys a 1 minute to read the screen, okay, and try to think in your mind, right, what we have discussed so far. Okay, so I'll give you the brief idea, right, whatever we have discussed in the last uh, 10 to 15 slides. Yeah. So what are the key differences between probability and non-probability sampling, right? So according to the slides that we have discussed, you all are aware, right? But let's discuss this like quickly. Okay. First is the selection bias, right? In case of probability sampling, right? Uh, Not the selection bias, the selection process. So in case of the probability sampling, we pick every individual randomly, right? And in case of non-probability sample, it is non-random, right? So the risk of introduction of bias in case of probability sampling, it is very low. but in case of non-probability sampling, it is very high, right? Generalizability in case of probability sampling, it is very high, right? And again, the statistical inferencing is possible here, okay? And here, in the case of non-probability sampling, the generalizability is very low, and again, limited to the sample itself, right? Because we are picking a particular segment, and again, whenever we choose something, it's based on some sort of pre-decided criteria, okay? So the use case for both of these, in case of probability sampling, so generally we use it for large or structured population, right? And non-probability sampling, we use it for the exploratory or hard to reach groups. Okay. Examples for probability sampling, the simple random sampling that we discussed, stratified, the cluster sampling. For non-probability sampling, we discussed about convenience, judgmental, snowball. Okay. So out of all these sampling methods we discussed, right, most of the time we'll be using the simple random sampling and the stratified sampling, right? Okay, so that's why I was saying, again, I'm introducing some bias. Okay, so but in general, we use these two methods. Okay, cool. Now let's move to the another slide. Okay, now which method should you use? Okay, if generalizability and accuracy are crucial for your task, then use probability sampling, right? If you need quick insights, or you want to perform some exploratory research, right, then use non-probability sampling. But again, I would say it depends, right? What kind of exploratory research you want to perform. Okay. For most of the exploratory research, you will be, using the probability sampling only. Okay. In data science and machine learning, probability sampling is preferred for training predictive models. Okay. As it reduces the bias and improves model accuracy. Okay. However, non-probability sampling may be useful in early research stages or when dealing with the rare population. Okay, good. Let's move to the next part of it. So the next part is the sampling distribution. Okay, so you remember we discussed about the probability distribution in our last class, right? So we'll be using the idea and the theory behind it, right? And there's a section as well. Okay, so what are the sampling distribution? Okay, a sam a sampling distribution is the probability distribution of a statistic. Okay, so the statistic could be sample mean, sample proportion, okay, obtained from repeated random samples drawn from the same population. Okay, so let's say if I am picking n number of random samples from the population, so each random sample can have a mean, right? So now what will be the distribution of those n means, right? You understood what are n means, right? We have fetched, or we have selected n random sample n. Okay, let me write it for you. We have selected n random samples, okay, and each sample can have n one mean, right? So n samples will be n mean. Okay, so if I try to plot it, like let's say the mean is like this moving, so this will be the distribution of your sample mean. Okay, and how we represent sample mean will be x bar. Understood? Because you remember we discussed in the initial slide, right? We represent sample mean with the x bar. So this x-axis is representing your sample mean. Okay. So now why is sampling distribution important? Okay. So it helps us understand how sample statistics vary from sample to sample. Okay. So you want to see, right? If you pick a sample, right? What is the mean of that sample, right? It will basically try to tell you, right, what is the difference between the two sample, and how will you check the difference, right? You remember when we were discussing about the uh like the statistics, right? Mean, median, mode. the measures of central tendency, measures of dispersion, right? These things helps you to decide, right? How these samples are different from each other. Okay, how sample statistics vary from sample to sample. Okay, it forms the foundation for your statistical inferencing, right? So in the upcoming lectures we'll be discussing it a lot. Okay, so it forms the foundation for your statistical inferencing, including your hypothesis, confidence intervals, right? So in the upcoming lectures we'll be talking about the hypothesis testing and the confidence intervals in detail. Okay, key idea. Even if we cannot measure an entire population, we can estimate population parameters using the sample statistics and their distributions. Okay, I'll tell you how, right, in the upcoming slides or in the upcoming lectures. Okay, cool. Now let's move to the next slide. That is the types of sampling distribution. Okay, so sampling distribution of the sample mean. Okay, okay, this is like very clear from the definition or from the title itself, right? As we are saying, sampling distribution of the sample mean. So the definition is the distribution of the means of all possible samples of a given size n. Okay, so what does it mean? Okay, so let's say from a population n, okay, we can create n number of samples, smaller number of samples, right? So here the definition is telling you the distribution of the means of all possible samples of a given size n. Okay, so the each random sample that you have created from this population n is having size n only. Okay, now, okay, so now what is happening, right? So let's talk about the formula. Formula for mean of the sampling distribution is, okay, here what is like mu x bar. Okay, what is mu x bar here is equal to the mean of the sample. Okay, so where mu is the population mean. Okay, this is the population mean. Okay, I'll tell you like how this is happening. Okay, so now formula for the standard error. Standard error of the mean. So standard error of the mean is this sigma x bar, okay, equal to sigma divided by the root n. Okay, here sigma is the population standard deviation and n is the sample size. Okay, yeah, key concept. So as n increases, right, the standard error decreases. Okay, if you go back, right, so let's say n tends to infinity, so your error will become zero only, right? Got it? Understood, right? Okay, so again, like, according to the key concept, as n increases, the standard error decreases, making the sample mean a better estimate of the population mean. Okay, for an example, suppose the average height of all the students in a university is 170 centimeter with a standard deviation of 10 centimeter. Okay, if we take random samples of 25 students, the standard error is, okay, so sigma x bar, we represent the standard error sigma x bar, right? So here, what was the formula? If you remember, sigma divided by the root n. Root n was the sample size. Okay. So 10 divided by the 25 will become 2 centimeter. Okay. So here, if you see, right, if I increase 20, like if I make it 100, it'll become 1 centimeter, right? So with if like let's say if I keep on increasing and so your sigma x will be reducing, right? It will be going down, it will be decreasing, right? So this means the sample means will vary, but their spread will be much smaller than the population spread. Okay. If you have any doubt, you can ping me either in chat or you can unmute yourself and tell. Okay. Now, the next thing is sampling distribution of the sample proportion. Okay. So what is the definition? The probability distribution of sample proportion P naught from repeated samples. Okay. Formula for mean of the sample proportion. We'll be discussing everything in the notebook as well. We have a Python notebook that I created for you. Okay, we'll be discussing that. So formula for the mean of the sample proportion will be mu p naught equal to p. Okay, where p is the population proportion. Okay, so formula for the standard error of the popular proportion is sigma p naught equal to root of p minus 1 by 1 minus p divided by the n. Here p is the population proportion. Okay, let's try to understand it using the formula. Okay, so if 60% of a city's population prefer electric car, so in this case, what is the proportion? Proportion is 60%, that is 0.6. Okay, and we take a sample of 100 people. Okay, so what will be the standard error, right? You know the formula, right? Sigma p bar equal to root p, that is 0.6, 1 minus 0.6, that is again p divided by the p, right? The total size of the population, right? That is 100 in this case. So your error will come as 0.049. So this tells us how much sample proportions are expected to vary. Okay. Now let's move to the next slide. Okay. Sampling distribution of sample variance. Okay. You remember I told you, right? We'll be representing sample variance with S square, right? So the definition is the distribution of sample variance is S square from the repeated sampling, right? The sampling that will be performing on the population. Okay. Key property, sample variances tend to positively skewed, right? Now you will tell me what is a positively skewed sample, right? If you remember, we talk about two types of skewness in your probability distributions or the distributions, left skew distribution or right skew distribution, right? So this is your homework, right? Well, all of you should remember what is a positively skewed sample or what is a negatively skewed sample, right? Or what are their properties, right? I want all of you to remember this, right? Because as I told you, right, we'll be discussing everything in detail. And we'll be like using everything, right? Because everything has some application in the whole lecture, right? From session one to session n, and everything is related. So that's why I want you to focus on each and every part that we discuss. Okay, cool. Okay. So the first property that we discussed, sample variances tend to be positively skewed, not normally distributed. Okay. So it follows a chi-square distribution with n minus 1 degrees of freedom. Okay. New term, right? We have not discussed about it, right? But we will be. Okay. So you can mark this. We will be discussing about the chi-square distribution. It's an interesting concept. Okay. And again, one more new term, degrees of freedom. Okay. So like with time you'll be getting to learn, you'll be hearing a lot of jargons, right? Like the skies per distribution, degrees of freedom. But don't worry, we'll be discussing about it. Okay. So formula for the expected value E of S square equal to sigma squared, the population of the variance of the population. Okay. Now let's talk about the properties of the sampling distribution. Okay, so what is the first property? Okay, the mean of a sampling distribution. Okay, the mean of a sampling distribution of a statistic, right, is equal to the population parameter it estimates. Okay, again, let me read it again. The mean of the sampling distribution of a statistic is equal to the population parameter it estimates. Understood? Any doubt? Okay. So here, if you like try to understand, we are talking about a particular statistic, right? It could be again mean, variance, proportion, right? So the mean of that sampling distribution we are talking about, right, will be equal to the population parameter it estimates, right? For sample means it will be okay, E of X bar equal to mu. Mu is what? the population parameter. Okay, here x bar is your sample mean. For sample proportion, again the same thing, E of P naught equal to P. Okay, this is your population parameter, this is your sample statistic. Okay, let's move to the next property, the standard error. Okay, so it measures the spread of your sampling distribution. Remember kurtosis? Okay, we talked about kurtosis, right? Right, and we talk about the spread parameters as well. What helps us to uh, measure the spread? What were the measures of dispersion? Remember, variance, standard deviation, right? So here formula for the standard error of the mean will be SE equal to sigma divided by the root n. Now you will tell me what is sigma and what is root of n here. Okay, I know you know it. Okay, formula for the standard error of the proportion SE will be under root P1 minus P divided by n. Okay, all of you remember these are the population parameter, right? Good. Key concept, a larger sample size reduces the standard error, making estimates more precise, right? So it's a very beautiful thing. I mean, or a common thing, if n tends to infinity, your standard error will become 0, okay, or close to 0. Understood? Okay. Yeah. So this is the most important theorem, I would say, for interviews. Like, it could be biased, right? But I have never attended any interview, right, where they have not asked about this or theorem. Everyone wants to know about, like, even in some form, they will ask you about the central limit theorem. It's the most beautiful algorithm we have studied so far in this series. Okay, so what is the central limit theorem? Okay, so the central limit theorem, and please listen it carefully. It's very, very, very important in a theorem. Okay, and if you miss anything, and like, please let me know. If you are not able to understand anything, please let me know. If you have any confusion, please let me know. Okay, so the central limit theorem is one of the most fundamental concepts in statistics, right? It explains how the distribution of sample mean. Remember, we discussed about it, distribution of sample mean or other sample statistics behaves, right? What it does, it explains how the distribution of the sample means or the other sample statistics behaves when we take multiple samples from the population. Okay, now let's talk about the definition in detail. The central limit theorem states that, listen it carefully, it's very important, right? Okay, this is the summary of your central limit theorem or the definition, you can say. Regardless of the shape of the population distribution, right? This is very important line. Regardless of the shape of the population distribution, the sampling distribution of the sample mean will approach a normal distribution as the sample size increases. Okay, provided the samples are randomly selected and the sample size is sufficiently. Okay, so here, let's say you have a population of size n, okay, and we don't know the shape of this population, let's say, because even according to the algorithm, it does not matter what is the shape of your population distribution. Okay, the sampling distribution, right, of the shape of the sample mean, right? So let's say you have created n samples out of it. Okay, n samples out of your population, okay, will approach a normal distribution, right? Now what you are doing, you are plotting the sample mean. Okay, so Again, read it carefully. The sampling distribution of the sample mean will approach a normal distribution as the sample size increases, right? The size of n increases, okay? Provided the samples are randomly selected and the sample size is sufficiently large, okay? Why CLT algorithm important, or why central limit theorem important, right? It allows us to use normal probability models for making statistical inferences, okay? Like confidence intervals, hypothesis testing, etc. Even when the population is not normally distributed, okay? So that was the first point, regardless of the shape of the population distribution, okay? It justifies the use of normal approximations in the real world application. Okay. If you have any doubt, ping me. I'll explain it again. Okay. Let's move to the next slide. Key components of the CLT. Okay. So what are the key components? We talked about two things, right? First was the population distribution. Second was the sampling distribution. Okay. So the population distribution can have any shape, right? Because it was a part of the definition only. Right? It could be skewed, uniform, exponential, bimodal, Poisson, anything. Okay. When we take random samples, right, the distribution of sample means will be normally distributed. Okay, as n increases. This is the condition. This allows us to make statistical inferences using the normal distribution. Okay, because we know the property of the normal distribution, right? We discussed a lot about it, right? So a normal distribution look like this: a bell-shaped curve. It will be symmetric around the mean, median, and mode. Okay, remember, right? And the thing will be the measures of even the measures of spread will be like a 60 empirical formula. If you remember, 68, 95, 99.95, 99.5 rule, right? One standard deviation away, two standard deviation away, three standard deviation away, right? If you forget, go back and study again. Okay, very important. Okay, now conditions for CLT to hold. Okay, random sampling. Okay, so the sample must be randomly selected from the population, right? So the sample that we are selecting, it should be selected randomly. Okay, there should not be, we should not select anything using the non-probability sampling method. Okay, everything should be selected using the probability sampling methods only. Okay, sample size, the larger the sample size, the better the normal approximation. Okay, so typically n greater than equal to 30 is sufficient. Okay, independence, the samples should be independent. That this means that one observation should not influence another. Remember, right, we talked about the independent events and the probability, right? I told you that everything that we are discussing will be used somewhere, right? So whenever we discuss something, and if you're not able to understand, then ask me out. Okay, let's move to the next slide. Okay, mathematical foundation of CLT, the central limit theorem. Okay, that's fine. Okay, so let acts as a random variable. Okay, representing individual data points. Okay, mu as the population mean, sigma as the population standard deviation. Like I told you, like in the starting only, right? We'll be representing the population mean with mu, will representing the population mean with the sigma, right? And x bar as the sample mean, correct? Based on a sample size of n, right? How we have calculated this x bar? It is based on the sample size, right? That was n. Okay. Give me a break of 1 minute. I'll be back. Okay. Yeah, let's continue. Okay. So what we were discussing, we were discussing about the mathematical formulation of the CLT, the central limit theorem, right? We talked about the terms that we'll be using, right? X as a random variable, mu as the population mean, sigma as the population standard deviation, x bar as the sample mean based on a sample size of n. Okay. So mean of the sampling distribution, right? According to the CLT, the mean of the sample means is equal to the population mean, right? We discussed about it in our previous slides as well. So E of x bar will be mu. Okay. Standard error, SE of the sample means same thing that we have discussed. Standard deviation of the sample means called the standard error is given by SE sigma divided by the root n. Okay. Sigma is the population standard deviation, S is the sample size. Okay. As n increases, according to the algorithm as well, as n increases, let's say till infinity, your standard error will become zero, right? So there's no standard error, it means you're reaching towards the population only. Okay, cool. So as n increases, the distribution becomes normal. If n is small, the sampling distribution may not be normal, right? N greater than equal to 30, the distribution of sample means will be approximately normal, right? Because this is like the cutoff, okay? Regardless of the shape of the original population shape, right? This is very important, and we don't care about the population shape, right? It does not matter because most of them will not be aware, right? What is the, you know, what type of distribution of population is following, right? And again, it's difficult to, calculate it, right? So again, as I mentioned initially, like it's difficult to even load that population data set, right? So it's difficult to show it what kind of distribution it is following, right? Could be right skewed, left skewed, we don't know, okay? And we don't care, right? So now the visualization of CLT, right? Let's try to visualize it using an example, okay? Example is rolling a die, okay? Suppose we roll a fair die and the values of that fair die will be 1, 2, 3, 4, 5, 6, right? The population distribution is uniform. Each value is equally likely, right? Remember, right? Because here each value is equally likely. The chances of selecting each value is almost equal, right? Because the probability of getting one is 1 by 6, 2, 1 by 6, right? Each and every number is having the probability of 1 by 6, okay? If it is a fair die, okay? Now let's take random samples of size n and compute the sample mean of each sample, okay? What happens when n increases? For n equal to 1, the distribution is uniform, same as the population, right? For n is equal to 10, the distribution of sample means starts becoming bell-shaped. Okay. For n equal to 30, the distribution is approximately normal as discussed according to the algorithm. Okay. Conclusion. Even though the original population was not normal, as I mentioned initially, the population distribution is uniform. The distribution of sample means become normal as n increases. Okay. We will see this in the Python notebook as well. Okay. So what are the practical applications of CLT? Okay. One we discussed, right? The statistical inferencing, right? So one very good example is the confidence intervals, right? We estimate population parameters using the sample means. Okay. Hypothesis testing. We use the normal distribution to determine the significance level. Again, terminology alert, right? What are p-values? Don't worry, we'll be discussing about it. Okay, you can make a note of it. We will be discussing about the p-values or the significance levels, right? Second application could be the quality control in the manufacturing, right? In industries, companies using sampling to check product quality, right? They cannot check each and every product, right? So what they do, they use sampling. Okay. And CLT allows them to use normal distribution even if individual measurements are true. Okay. Medical research. Statistics have a lot of application in the medical research. So in drug trials, researchers take multiple patient samples. CLT helps estimate the average treatment effect reliably. Okay. Finance and economics in stock market analysis. Analysts take average returns over time. Despite daily fluctuations, long-term averages tend to follow a normal distribution. Okay, see, this is the real life example you can see, right? Okay, even you can go there and check online. Okay, so now the key takeaways. Okay, CLT states that sample means follow a normal distribution as n increases. This is the required criteria. It applies regardless of the population's original shape, right? As we discussed, it can follow any distribution, right? Does not matter, right? The standard error decreases as the sample size increases, like because n is a denominator and tends to infinity, standard error tends to zero. Okay. CLT is fundamental for statistical inference, allowing the use of normal approximations. Okay. Summary table. Shape of sampling distribution, if n is less than 30, similar to the population. If n is greater than or equal to 30, approximately normal. Okay. Standard error, if n is less than 30, it will be large, right? But if n is greater than 30, more precise estimates, right? And let's say, as I told you, if n is still going towards infinity, it will become zero. Inference accuracy, if you're taking sample size less than 30, it'll be less reliable. If you're taking a bigger sample, it'll be more reliable. It's common understanding, right? If you're taking small samples, right, you'll not be able to, make proper judgment about it, right? Small samples are having very limited application, but large sample size are widely used in statistics. Okay. So let's talk about the conclusion. The central limit theorem is the foundation of statistical inference. It allows us to work with sample means even when the original data is non-normal. Okay. This makes confidence interval hypothesis testing and prediction modeling possible. Okay. This is the very important concept. That's why I was telling you, right? This is helping us to, model the confidence intervals, hypothesis testing, prediction modeling, everything possible. Okay. Yeah. Summary and key takeaways from the lecture. Okay. Sampling is crucial for making statistical inferences without studying the entire population. The reason is studying the entire population is a very costly affair, right? It requires a lot of computation, right? Probability sampling methods provide more reliability and generalizable results, right? Because non-probability sampling methods introduce a lot of bias and non-generalizable outputs. Okay. Sampling distribution helps understand the variability of sample statistics, right? The central limit theorem is fundamental for inferential statistics, ensuring normality in the sampling distribution for largest. Okay. So we are almost out of time. So what we can do, we can discuss the Python notebook that I have prepared for you guys in the next session. I hope everything is clear. If you have any doubt, make a note, go through the video, try to read everything. Okay, try to understand. If you have any doubt, we can discuss it in our next lecture. Thank you everyone. Thanks for your time. Have a nice evening. Bye bye.